Hello and welcome to today's Wolfram Institute live stream. Today we're joined with Matthew Fox, aka the Memes of Destruction. He'll be talking about units, units of measure. Uh, he'll give a brief overview of their history, and we'll talk about how they connect in with the Wolfram Physics Project. Matthew, thanks for joining us.
All right. Thank you for having me.
So go ahead and get started.
Jump into it. All right. Let's bring this up. Should should work. We just did it before. All right. Should be should probably actually go to the top. There we go. All right. Can everybody see this crazy wheel diagram and maximally entangled Professor Wolfram?
Yes, yes, we can see it.
Okay, okay. So this was the hero image from the project and everything. So basically this wheel right here is the current definition of SI. Dugan has brought it to my attention that as of 2030, they're planning on redefining all of this in terms of the second. That makes a lot of sense because we got some really good clocks, and you want to have whatever your basis of the units are on the things you have the most confidence in. Because with the 2019 redefinition, like I didn't even know. I was working on some stuff and I was looking at some numbers and I'm like, well, the data listed here is different than what's listed on Codata right now. I had no idea why. Minor investigation, I'm like, oh, they updated this the unit system or the definition of SI in 2019 and they were rolling it out. Hence why certain things were changed, and then you have additional measurements and everything where they're trying to provide the most precise based upon a number of measurements and everything for different constants of nature, which now, for the most part, our units are defined off of here. So basically, we can see here, we'll get into this a little bit further here. Um, Basically, one of the other things that I basically just said out loud what was already defined within the Wolfram Physics Project um, schema, so to speak, was that they have this term here, this zeta. What the heck is a zeta? Well, it's defined within the physics project as elementary energy divided by elementary time, which we have a scaling factor that we're going to get into that's different than this. It's basically G, uh, and it's basically whatever you have that as, you would be scaling Planck units, and that's how they go by it. But the thing is, if you have an elementary energy divided by elementary time, it's going to give you the maximum of power. So it doesn't really matter what that is. So that's why I have Stephen all entangled here and a double cover, so to speak, of some hypersurface here. Um, and there's some interesting little tidbits once we get into this here. But I mean, I could just read through all of this. It's note. This is a new version. The previous version that I know some of y'all had gone through before, some stuff was just wrong. And then when Dugan had messaged me, he actually inspired me to go back, look at these things, go make those corrections. And I actually did add in another section because I kind of feel like I missed the plot, so to speak. The whole main connection was literally sitting right in front of me, and I completely missed it until this past week. So thank you, Dugan.
You're welcome.
Um, so, so basically, our bases in SI, we have 7 base units as of now. So the bases are the meter, which is a unit of length, the second, which is our unit of time, the kilogram, which is a unit of mass, the ampere, the unit of current, the Kelvin, uh, the unit of temperature, the mole, it's the unit that's counting and everything. It is an amount. And the candela, which is luminous intensity and actually still, it has a little bit of a reference to some of the SI units because it does have time in there, but it's ultimately attempted to reconstruct what a human would see for a single candle, which seems kind of crazy, but then again, if you are selling candles and you want a certain luminous intensity, well, you want it to actually be advertised right. Or if you have one of those like 1 million candle power flashlights or something, that's kind of fun sometimes. Just don't look directly into it. Okay. So basically, it's a quick overview of the summary of basically we have a particular factor here, that G factor there, which is basically this little thing over here. If I'm mispronouncing that at all, please correct me. I believe it's capital G, is pronounced. Um, but basically, there's this particular factor that the original estimates were done calculating the estimated age of the universe and using some logarithmic recursion factor and everything. Long story short is I attempted to do something. I was off by 17 orders of magnitude. Xerxes gave me a pro tip at lunch. And then after having my mid-project meeting with Steven, he assigned me homework. So then while doing my homework, I'm going through and I'm reading over space and time like hypersurfaces and stuff. And we need to have some notion of flux through our hypergraphs here and everything. And I go back and look at the calculation that I had done at lunch after Xerxes gave me the idea. And I'm like, according to Wolfram Alpha, this dimension or interpretation is flux. I'm like, that's interesting. What if I took that seriously? So long story short is I went in, I basically just stripped the dimensions out, which seems like a very reckless thing to do, and then it seemed to replicate a lot of the initial physics project findings within approximately one order of magnitude, which I mean I wasn't expecting that. Um, but again, this is a speculative connection, but we're gonna kind of break it down. All right. How the heck did we get here? Okay. So again, as it says, story of units is extremely vast, detailed, and I'm not going over everything here. There's large amounts of history that we do not cover. I think it's worth covering. And if you haven't looked into this, some folks are like, we just have these random units. What's the meter? It's like growing up, I'm like, oh, it's a little more than a yard because my reference is an American here stateside. It's like we're still imperialists, so to speak. We still use the foot and everything like that because reasons. I don't know. Um, but ultimately, as certain units here seem to be uh, arbitrary, they seem to get a little less arbitrary over time. And there's some interesting connections we're going to go through here. So sometimes you'll hear the saying, you want the right tool for a job. Quick aside, I used to do maintenance. I'm not saying I'm a good maintenance guy, but I'm just saying I did used to do it. And you can use a screwdriver to screw something in. Now, that might be applicable if you're using something like if you're doing like a lock set or something. You want to have very precise motion and everything. If you're trying to screw in some drywall into some studding, you're going to want a power drill because because otherwise, good luck, good luck. So it's kind of like you can build a house with an old school hammer, nails, and saw, but if you have a table saw and I don't know, a nail gun, you're probably going to do it a lot faster with a lot less headaches. So that's kind of how I look at a lot of stuff within the Wolfram language. Could you do all this stuff out by hand and stuff? Sure, you could do that. But why wouldn't you leverage the computational tools we now have available? And that's basically the only way I was able to do any of this. So thank you, Team Wolfram. Uh, but basically, if you're talking about units, I'm just going to read this quick example. So if you require something like a recipe, some of us may have culinary skills, some of us may not. But I'm just going to read this because I think it was stated decently well. So perhaps one requires 2 cups of flour for a recipe. With a requisite flour available in a unit measuring cup, no big deal. You just fill it up, you put 2 cups in, you're good. Now, however, if one does not have the requisite cup, then one may default adding 32 tablespoons of flour because 1 cup equals 16 tablespoons times 2 cups. If one has neither a cup nor tablespoon but a teaspoon, one would have to add 96 teaspoons of flour because 1 cup is 48 teaspoons times 2 cups. If one is unfortunate not to have any standardized measure, so to speak, then the age-old method of eyeballing may be applied. Good luck with that. I'm not good at that. As somebody like myself with no culinary skill, this may often lead to disastrous results. But it is a simple single example of a simple measure of volume. This is something that we often may come across just to kind of get it in our heads. And when you're starting off with units, we literally had them based upon human characteristics. So you all may have heard of the unit per qubit, not the modern quantum computing kind, but literally the qubit was the length of your arm to your fingertip and everything. Now, over time that would change, but to an observer like us, it's probably going to do pretty well. And people for hundreds, probably thousands of years have literally, actually it has been thousands of years, have used that as a basis of measure because if you're building a house and you have a reference, oh, it's about 1 qubit, or it's about half a qubit and stuff. If you're using rough elementary tools and everything, you can probably build a house, have a successful farm, and have a living. Fantastic. The issue you run into is, again, it's a human basis, and we're all different. So, since human beings come in all different shapes and sizes, my qubit's likely going to be different from your qubit and everything. So, one of the big things that we came back down to was we needed some method of standardization. And there's some very interesting ways that they went about this. So you also have things from the imperial system like the hand and the foot. So the hand is often still used to measure the height of a horse. Um, the foot is still basically one of our standard units of measure here in the States as well. One of the interesting things that you come across here is people realize that everyone's different. So some of our British friends apparently had the great notion of let's utilize a standard distribution. So I'll just read from this part. So early methods to account for such variation led to the British rod, based on a randomized collection of 16 different men's feet. While we may credit those utilizing the power of a standard distribution, the problem here is still plainly evident. What sample are we taking? Are these folks all from a similar lineage of large-footed folks, so to speak, or vice versa? Because that's going to end up skewing your results. Because again, it's literally based upon a human style metric.
Yeah,
So
I was gonna
most of the
ask about
standard,
that if I may.
yes,
So
please.
like the qubit, like it's from your elbow to your wrist, right? Or to elbow to tip of finger.
I believe it. I believe it's here. I believe it's the shoulder to the tip. Hold
Oh,
on,
it
let me
doesn't
just go
matter. It
back
said
here.
forearm, but in any case, whatever it is, it's like there's going to be a variation in the population of that length. And so, like if you have a short arm, you might think, okay, we'll have a shorter cubic than the average. So like you kind of account for that. Or if you're longer, then you say like, okay, well my cubit's probably longer than average, so like you can kind of account for that. I remember Veritasium doing an experiment asking like coming around with a jar of like marbles or something, right? And you guess the number of marbles in the jar, and you ask a bunch of people, and the average is pretty darn accurate to like the true number. So if you know, on average, people are good about knowing what the average is, let's say. And
Yeah,
it's
no,
it's
I
interesting
think
that
that's
also that they had a standard measurement thing like pick 16 people at random, uh, hopefully 16 average people, quote unquote, and then like take the average of that, and that'll be pretty good for most purposes.
a lot of folks in the past, like a lot of these folks are really smart people just because it's like they obviously saw that this was an issue and they tried different ways of accounting for it. Now, it's much easier to account for it when we have modern technology and we're literally like remote viewing this presentation at near the speed of light across the earth. I mean, that literally is like magic if you went back like a few hundred years. But this is where I like to invoke Arthur C. Clarke's any sufficiently advanced technology is indistinguishable from magic. Now, you may or may not believe that, but I think that might help put different things in perspective. Um, cool.
Yeah.
Anyone else? All right. We will continue. All right. Let's see. Okay, we went through that. Blah, 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 blah. Okay. So ultimately, when human beings are interacting with one another, you could say, oh, well, this was so and so's Cupid, or this was so and so's Cupid. But once you start exchanging things like goods or services, like here's some flour, here's some rice, I have a goat, or something like that, it's, well, how much are we getting? So you would need some form of weights and measures to account for this. And that's where standardization comes in place, mostly from commerce, and then as we continue through, very often towards more scientific explorations, because the unit system that we currently have right now will get into how they are defined, which is interesting. And my more recent dive into it helped me realize that I'm like, okay, one, algebra is awesome. Number two, um, there's a logic for it. Now, you might not always agree with it, but this seems to be the best we have in order to reference things. Because once you set a basis and you begin to relate it to other things in a coherent fashion, that's ultimately the big thing. Because once you start relating different things through that coherent system, there may be different units and everything, but if you can get a dimensionless magnitude, so something like the electron is about like, was it like 9.1 times 10 to the minus 31 kilograms or something like that. What the heck does that mean? But if you put it in reference, once we use the kilogram to something like the Planck mass, that should have a magnitude relationship because you could divide the dimensions out. And those dimensionless uh, quantities are something that's really telling. And I know at the summer school, Dugan, you had mentioned something about like the fine structure constant. And I just remember just from playing around and hearing some other folks that normally it's defined as elementary charge squared over 4 pi epsilon naught h bar c. Now it's maybe you have a good idea what that is. I could try to imagine what that is, but it's a very important dimensionless number. If one takes a quick moment and thinks that through, you're like, it's elementary charge squared. That means whatever's in the denominator has to be also charge squared. The associated charge happens to be the Planck charge. So you're taking an elementary unit of charge of either the electron or the proton, dividing it by a limit of charge, and then you would find that amplitude, you square it, and then you would get your standard probability, the fine structure constant, the about 1 over 137 that we all know and love. Okay. So that's part of where I kind of wanted to do units to even see if some of the things that I was playing around with were even justified. Um, Still working on it. But we come over here. All right. So now we have our actual little wheel over here, and this is an additional thing that I totally forgot to put over here with the actual uh, symbols and units. So let me embiggen this. Okay. So as we can see here, we have our SI base units, and then we have our derived units. So it's relating these things by multiplication and division. So solid lines are multiplication, dashed lines are division here. There is one note here that certain things kind of bother me. This is, and again, this is a personal opinion here. Angles, if we look over here, it literally just gets defined in here. So it's like you get radians, which is a two-dimensional version of angle, and then yeah, another dimension in there, and you get steradians, and that goes into lumens, which lead to luminous intensity and everything like that. Uh, I personally think it should have probably been related to the meter because you don't really have a notion of angle without a notion of lengths or relating two different lengths there. So again,
Right,
that's a
right.
personal
Yeah, the
opinion.
radian is you have a circle and you're measuring distance around the circle based as a ratio of the distance of the radius. So how many radiuses around did you go?
Right, right. So as we can see over here, we got our meters, our kilograms, our kelvins, our candela, our moles, our amperes, our seconds here. You can see how they branch out, and uh, as Dugan, I know you'd sent me before. We had the update that they're going to do is they're going to base pretty much most everything off of seconds, and that's probably not the worst idea. As we can see, this it's all over the place. It's going here to our meters per second speed. We've got our acceleration meters divided by seconds squared. We invert seconds, we get hertz. It goes to the watts, the becquerel, the Weber, and everything. Oh my God, I'm actually remembering a lot of these units. It's I guess if you look at them long enough, they it starts to sink in. It's kind of like, I don't know, times tables or something. Sometimes it just kind of gets ingrained in you. But as we can see here, the second and the meter are extraordinarily used here. Now, you could make the argument that, well, the ampere, it is literally defined by coulombs divided by seconds. One could make an argument that, all right, maybe we should have charge as that right there because it's relating charge to seconds right there. So um, again, as long as it's coherent and we can go back and forth, things should make sense. Um, if any mathematicians here have a nice way of saying, well, within group theory or set theory, it's because of this reason, I still don't know. I'm just, we set references, we relate the magnitudes, and it seems to work exceptionally well. We've been able to build technology that where if you can actually build it, the proof is in the pudding, so to speak. So, questions? All right. Let me move this back to normal size. All right. Oh, and part of the reason why I did this whole circle thing was it looks like a hodgepodge, and this was kind of done intentionally because normally they have just the straight down units and everything. On this website, they actually have a nice little circle. So I'm like, all right, let's recreate this. Um, so it almost kind of looks like one of those diagrams where you're connecting all these different ideas and everything. So it kind of almost looks like, what the heck are we doing? Somehow it works. That's the amazing part that I was kind of trying to communicate.
Hmm.
All
We
right.
have a question from chat. Damaros is asking, isn't Kelvin also connected to other units via gas laws?
That is true. The
Hmm.
oh my God, I think I actually did make a mistake here because Kelvin
Oh,
should be, well, you can convert it to pascals and everything there. Yeah, no, the absolute gas law. I think that's how we originally defined the concept of absolute zero, which is like negative 273.15 Celsius, aka 0 degrees Kelvin. Um, yeah, it's amazing that that stuff seems to work, but yes, it is. And then we get into um, I believe that's more of a statistical mechanics thing because we're saying, okay, what are the total possible number of microstates and everything? And we'll get into that once we get there. And our good friend Boltzmann was definitely ahead of his time in a lot of ways, and unfortunately, not everybody was as forward thinking as him, and he got ridiculed to the point where, unfortunately, I believe he ended up taking his own life. And one of the things that I think is worth pointing out here, as far as a lot of the history of science goes, is a lot of times we'll be taught these different concepts, and it's like, oh, these people, they were inspirational figures. We hold them in such high regard and everything. And you look back and it's not the only occasion where somebody posited an idea, were ridiculed highly, and sometimes some of these revolutionary folks, they literally died penniless and alone. So is that the price for forward thinking at times? Have things changed? Hopefully. Okay, I'm sorry, that was a little bit of a rambling response
yeah.
there,
I
but
guess I'm looking into it. The Kelvin is somehow related to joules, so you
it
gotta
is
start
well,
with
it is through
joules.
Boltzmann's constant because
Uh-huh.
you divide it by Boltzmann's constant. It's an energy equivalent.
Yeah.
It's how we translate from temperature to energy and energy to temperature. It's the little gate there. I always forget whether it's multiplication or division. Um,
We have another question.
thankfully, go on.
Do we really need the candela? It's a measure of
I'm gonna. The following is an opinion. The candela infuriates me for certain reasons, but then again, there's a logic to it. The candela, I believe, is part of the whole commerce thing where um, I remember some folks were making a big deal like a few years back. It's like, oh, the EU regulates like candle wicks and stuff like that. I'm like, well, you're buying something that's supposed to provide luminous intensity. You want it to actually be the actual intensity that you're actually purchasing, right? So I believe that's kind of more of a commerce thing as well. See, it's a measure of brightness, but it's literally tuned to the human because it's like 1 over 163 to try to take in our vantage point from a candle at X. It's measuring plane angles and stuff. I'm gonna say, let's hold on for my rant once we get to the candela. We'll get into it more in a little bit, but that during the project, it just when you see the definition, you'll feel my plight.
the
But
commenter is
as of
saying
now,
that
it is
it's really is tragic, the story of the candela or whatever. I think they share your sentiment.
it's it's
But you're
okay.
right. If it
It's
comes from
okay.
commerce, I mean, commerce is like the got to get things accurate, got to get things fair. Everyone wants like equality on the transaction about what's being purchased for what amount of money. For, like, how much candle
Right.
am I getting? I mean, people had to come up with something.
Yeah. Oh, and for other things, just even precision and everything. If I used to kind of be a bit of a motorhead myself and everything, and you're hearing about you're boring over a manifold to get this much more, like by like half a millimeter or something like that, and you're gonna get all this more power out of that because why? There's no replacement for displacement. That's
Right.
it's a very American thing to say. Okay. Following question. I'm sorry, I don't have chat up right now, but uh, feel free to stop me at any time. All right. So the meter. Okay, it is our SI unit of length. It was originally defined as the distance from the North Pole to the equator by root of Paris, of course, divided by 10 million. I mean, shouldn't that be an obvious thing? It's you you hear that and you're like, why the heck are we using it? That seems like the most arbitrary thing. In actuality, it wasn't necessarily the most arbitrary thing because we had notions about how large the Earth was and everything. And if you're going to put something in reference, it's like, okay, you could do a human thing and say it's okay, it's like one big pace, but then you still run to the other thing. It's like, what do we have in common? Well, we all live on Earth, so it's like, let's use the Earth as a reference. Um, so to be fair, it was based upon, yes, and it's probably a little less arbitrary than the summation of men's feet. So that's that seems to be a thing over there. All right. So, officially in 1960, during the 11th General Conference on Weights and Measures, the formal definition of the meter became length equal to 1,650,763.73 wavelengths in a vacuum of the radiation corresponding to the transition levels between 2p10 and 5d5 of the krypton 86 atoms. So, again, that's, of course, people understand exactly what that is. Um, the interesting thing here is we're measuring this via an atomic clock. Atomic clocks, as we'll get into, end up being the basis for time. It's a very interesting thing, in my opinion, that a lot of these measures of length and time, or at least with time, we're utilizing a length, or with length, we're often utilizing a time. So it's just something I have in the back of my head, and it's an interesting little tidbit. In 1983, basically, we nailed down the speed of light to its current nine significant digits, 299,000, excuse me, 299,792,458 meters per second. And when we go through how this is defined, it's an interesting thing because it's defined as 1 over the magnitude of c. So basically, we're doing that, and then we're literally defining the meter as the one of that.
Yes, that's one
We're going to
second
show
over
this.
C.
Yes, yes. Because the way they end up doing is they'll take the numerical value, divide it by C, and then literally put in seconds there because now we're dividing seconds by the hyperfine transition frequency of cesium-133, and then you set it equal to 1 meter. And that's what it comes. So basically, what they do is one of the versions that they officially do it to. This is the equivalence of that other method there. So basically, you take the numerical value, the hyperfine transition frequency of cesium-133, you divide it by the numerical value of the speed of light, and then you multiply it by the speed of light divided by the transition frequency of cesium-133. So you take the numbers and then you multiply them, and it comes out to be 1 meter because algebra is awesome.
'Cause that's
It's
how it's defined. Yeah.
it,
So like these cesium
it's
atoms, these krypton atoms, what's good about them is like you could get them vibrating, and it's very specific peak of vibrational mode that it'll land on, and it'll be the same across different atoms. So as long as you have one of those atoms vibrating at that particular mode, you got a really good reference for frequency. And then with the meter, it's like, okay, well, it's emitting radiation at a very specific frequency, uh, and the speed of light is that we know from relativity is going to be constant. And so you can take a number of those wavelengths, count them up, and then boom, you got a meter.
I mean, it's an amazing thing that we've even been able to conceptualize something like this because you start going through and you're part of it, it's like occasionally you just want to say that's completely crazy. But then people build amazing things and you're like, is it is it really crazy or are we just kind of just following the logical process to the best that we can within the realm of science as we know it? So, me. I do think I should probably share. Where was that? I have. I just want to go over that whole. Let me unshare this so I can actually do my links. Uh, just one moment, just because this is a fascinating thing when you actually go through it. Um, because this was one of the things that I actually missed the first time going through was going through like most of the stuff was off of NIST website, and you actually go through. I'd gone through some of the other guys over there. Hold on. This guy, and move it over here. Okay, we'll share this guy. All right. So let me bring this guy up. And these are how it has been defined as of 2019. All
Um,
right.
oh,
Here we go. All
oh,
right.
nice.
So we go down, and this is also available in French.
Of course
They
it
go
is. Yeah.
through. So kilogram. No, Planck. So I found it. Okay, so they have the units there, and then we go through the derivation. Okay, let's embiggen this a little bit. All right. So as we can see here, the meter, with our French spelling, in the SI unit of length is defined by taking the fixed numerical value of the speed of light in a vacuum C to be the value we stated when expressed in the unit meters divided by seconds, where the second is defined in terms of cesium, the frequency of cesium. Okay. This definition implies the exact relation C equals uh, the speed of light in our units meters divided by seconds. Inverting this relation gives an exact expression for the meter in terms of the defining constants. C in the transition frequency of cesium. So as we can see here, we got I had that wrong. Uh, I thought they put the numerical value up there, but basically they take C divided by numerical value, put in seconds, which is defined by cesium, and we get out 1 meter. Or as I put in the project, I should probably add in the other versions too. Um, basically, the numerical value of cesium divided by the numerical value of the speed of light, and then you multiply it by the speed of light divided by the frequency of cesium. Gives you this value here. You put those in those units, and basically it should come out to be the same that 1 meter. And we go through a very similar thing when we're defining the kilogram and everything. But at first, I'm like, this seems a little reckless, but they seem to be pretty careful here because I think they only have one thing that they're solving for at a time. So once you've set these limits here, or these bases, if you would, for measurement, you start having, we can get out the kilogram because now you have Planck's constant divided by the numerical value of Planck's constant. If you've got the meter defined by the speed of light, the second defined by cesium, now we can get out the kilogram. And then we just continue on through that as well. And it's, I don't know, it gives me a greater appreciation for mathematics, especially things like, I don't know, like linear algebra and stuff. So, question.
Right. So I guess
Nope.
what the cesium atom is doing is we're saying it oscillates at about 9 gigahertz.
Yeah.
Okay. So we're defining the second based on 9 billion or so oscillations of a cesium atom, and then we're using that to say, okay, well, if that's 1 second, then however far light goes in a second, that's going to be um, about 300,000 meters.
Yep. So as you can see, basically just what you said there is you have cesium itself, the value of the hyperfine transition of cesium. So like you said, about that 9 gigahertz there. We take the numerical value, we literally just divide it out. That gives us 1 hertz. The inverse of 1 hertz is 1 second because 1 hertz is 1 cycle per second, which will yield out this, which it's a fascinating thing that these things seem to work so well. And I'm like, well, what if we change it to something else? Um, and I was looking for other random coincidences, and I'm like, oh, there is a cesium 137, but I'm like, is this the unit closest uh to what is it, element like 137? Because there's another one above it there, but I apparently it doesn't work quite as well. Again, I'm not a chemist or anything. I might just be putting a whole bunch of hogwash out there with that, so I'm just speculating. Sir, it
Um,
looked like you had a question.
oh, I was just thinking
Okay.
about how, you know, there's also a variation of temperature of that cesium atom having an effect on its frequency, or there's they talk about clock drift in precision timekeeping. Uh,
Because I see Brian is commenting that we could use G, the gravitational constant, and integer number of atoms. Um, would that?
hmm.
Oh. So the frequency of oscillation there. I'm trying to think how you design. Okay, so you could measure. I don't know. I don't know enough to comment intelligently on
Hmm.
that.
Nor do I.
Okay. All right. So
Damaris is
let's.
asking on YouTube, how did they get the Planck constant? Is that also from the cesium atom properties?
So the kilogram is defined off of Planck's constant. So basically, Planck's constant before the 2019 redefinition, it was a measurement. We had it to about 12 significant digits. The only reason I know this is because I did some calculations using all the digits. Um, when you looked at the previous measurement, the last two digits, there was kind of a large error there. So during the redefinition, they just lopped it off and defined it at 10 significant digits. It's like, all right, we have extremely high confidence that Planck's constant is this to 10 significant digits. Once we got past that, it got a little, there was more uncertainty. So speed of light is defined at 9 significant digits. We got Planck's constant at 10, hyperfine transition frequency of cesium we have to like 10 significant digits. So it's lining up in ways that, okay, we have these magnitudes to a certain precision. If we define them at this, um, then we should be able to go through and translate out. So Planck's constant is like right here. So basically, we take the numerical value of Planck's constant, divide it into Planck's constant. We have the meter. as defined by the speed of light. The second, defined by the hyperfine transition frequency of cesium-133. And then you just would solve for x, or x kilograms, and it happens to be 1. So, and then you can go through if you want to do all the stuff out here. You can do this, but it's I just find it fascinating that math works so dang well. I don't know. It allows us to do some really amazing things. So let me go back over here and share this guy back over here. All right. Okay, where do we go? All right, I went through my. All right, I shall accelerate a little bit, pun intended. All right. So, okay, as we could, meter. Okay, so we cover that. All right. So the second, originally, it's just 1/60th of a minute. A minute is 1/60th of an hour, 24 hours a day. It's like it really appears to be like an earthly convenience. It's like meter, it's like North Pole to the equator divided by 10 million because that's obviously what it is. The second, it literally is an earthly convenience. However, this actually came from astronomy and a lot of ancient astronomers, where I believe it was the Sumerians who were some of the first folks to divide the sky up into like, or the circle into 360 degrees. And then you'd have the Egyptians and then other folks like in China and everything to basically start to subdivide those up into minutes, hours, seconds, things like that. Minutes and seconds, I believe, for astronomy, because those are literally still the units used because, well, it's mod 60 or mod 12. Um, so basically, you have 360 degrees, you can divide it up by 60, which is a very useful thing. And a lot of folks have argued, oh, maybe we should use like a mod 12 system or something. Uh, but it's just, I find it fascinating that all these different things throughout history and just get built upon, and it seems to work extraordinarily well. So we went through a number of different times. We had sundials in Egypt. Uh, Egyptians and Chinese folks of the past basically would use water clocks, which seem to work pretty well. And then you'll eventually get things like hourglasses and everything. Um, and again, for mechanical clocks came around in Europe around the 14th century, improving with spring-based technology in the 1700s. Huygens helped develop the pendulum clock, and basically it ended up being adopted as a timekeeping standard. It is interesting because if you have the tick-tock of a grandfather clock, well, you have the frequency of a particular unit of length and its oscillation. It's just again something useful to keep in the back of our heads, I would claim. Okay. So basically, as we continue to get more and more precise atomic clocks and everything like that, our precision increased. So now we have the modern SI definition, like we were just going over a couple minutes ago, where it's literally 1 over hertz times the hyperfine transition frequency of cesium-133, which comes out to be 1 second. And again, some of this does seem very redundant there. It's like dividing by 1, just taking the number. But if we follow it through and we have defined units, they're no longer a variable. It now has a defined definition. Now, maybe that definition is off. Maybe the true number for a lot more decimal places, maybe we'll never be able to know. I mean, hopefully, and if anyone's been paying for the Wolfram Physics Project, we're at least attempting to find ways to figure out what's going on to help, I don't know, just our own curiosity and ultimately probably to hopefully better humanity. That would be a nice thing. All right. Questions on the meter. Don't worry. We can come back to this. Let me see any other chat questions.
Good.
Okay.
But yeah, it's no surprise that one unit keeps coming out of these. I mean, when you plug in the sort of the definition of the unit back into like a fraction that is related to that definition, you're going to come out like everything cancels and you just got like that unit coming out again.
It's it, I almost view it in again. I very very noob coder and everything, and even in my acknowledgments, it's like yes, the Wolfram Notebook assisted and GPT 4.0 definitely did assist me. And now it's like you go through that, and it's like, well, I need to edit this, and so now you need to physically get into it. So basically, my whole point is it's kind of like code in a way. It's like it can be frustrating as heck, but when it works, it's a beautiful thing.
Well, when it works, it means you've got onto the definition. You understand it. Yeah, absolutely.
Mm. All right. Or maybe we just got lucky. I, I,
Or maybe we just
I don't know. Who knows? All right. So our friend the kilogram, our unit of mass, it was originally codified as the grave, perhaps not the best name, which was defined as the mass of 1 cubic decimeter of water, or 1 liter, at the point where water would begin to freeze. Coincidentally, this relates the mass of the kilogram to the meter, which was an interesting thing. And the conventional density of water right now is about 1 cubic meter, is approximately 1,000 kilograms. It deviates in like the third decimal place. Uh, Technically, one could imagine that at the right pressure and temperature, it would be exactly 1 cubic meter would equal 1,000 kilograms, which is kind of a cool little thing there. So,
huh, okay. So
um,
no, that's interesting. I never really thought about like the temperature aspect of it. So it's like you have this certain volume of water at a particular temperature, um, and then that mass equals 1 kilogram.
yeah. Or I mean, like you could be a certain point below the surface of water. You would have around it. There's going to be maybe like a gradient as you're going through there. But I mean, that's kind of a cool little thing that, well, they're actually, at least initially, the kilogram was related to the meter in a way. So I thought that was
Well, you
a
use the
pretty neat
length to
thing.
define the volume.
Right, right. But and again, one of the things are this was 17, 1800s and stuff. It's climate control wasn't really a big thing then, so it's like, well, water can freeze. So some folks would use like maybe I think some Chinese folks would use like alcohol or wine or something like that because its freezing temperature would be lower than water to try to keep track of things. But people did a lot of really creative stuff to try to figure out what's going on.
Well, I guess the
Okay,
thing
so
there is like, okay, sorry for going into this a
no,
little
no,
bit
no,
more,
go.
but like if water expands when it gets warmer, like a lot of other substances do, then if you had like a particular amount of water in a jar filled to the top, and then you heated that up, it would like push out, and then some of it would spill out of the jar, and then what's left in the jar, even though it's still full, it's warmer, so it's like has more expansion. It's less mass because some of it's spilled out. So that's why you want to set the temperature, saying, okay, well, at the freezing point, the amount of ice water in this like volume equals 1 kilogram.
Yeah, no, no. Water is a fascinating uh, subject of study. I interviewed a gentleman who, during the pandemic, he was supposed to do lab work, but he wasn't able to do lab work. So he spent 3 years going over the past 60 years of history of water. And it's like there seemed to be a particular, I think, is something to do with like the Young's modulus and translating. Basically, water was doing things that it didn't seem. You wouldn't we folks like us, an average person might not believe that it would be able to do. It had certain properties that were discovered independently by several different teams that apparently had no collaboration with each other. So I just found that that was an interesting thing, fascinating subject. Um, okay, so ultimately we had the kilogram of the archives, where this was one of the first versions of a 1,000 gram platinum cylinder as the standard. We had the meter convention in 1875. So that's where we got the IPK, the platinum iridium cylinder that even when I was growing up learning science, it's like, we have this thing. It's in France. Don't drop it. It's literally our unit of reference mass that we use to help calibrate all these different things. And it's like, okay, that's a cool thing. Like growing up, that's literally like what I was taught and everything. Um, Basically, the more modern definitions help were brought to us by Brian Kibble from the UK's National Physics Laboratory. Uh, so basically, the Kibble balance is you put a weight on a press, and basically it's recording that mass as weight, and then basically you would relate it to the gravitational constant of Earth, like our about 9.8 meters per second squared. Uh, so we have that, but you can use electrical force, so to speak. I'm using that in a broad term there to try to balance it. So basically, uh, let me just actually read it. Uh, the Kill balance allowed us to weigh objects by the local gravitational effect and offset by the amount of power in watts required to make the scale balance, where the mass in grams is equal to current times the magnetic field strength times the length of the wire in the coil. This precision was limited by one's knowledge of the magnetic field strength and length of the coil. However, physicists leveraged two constants of nature, the Josephson constant, K sub j, which is two elementary charges divided by Planck's constant that relates voltage to frequency, and the von Klitzen constant, which is Planck's constant divided by elementary charge squared, that describes the way discrete values exist in electrical resistance. Uh, Now it's basically in 2019, it's defined by Planck's constant using the method below, which is basically Planck's constant divided by Planck's constant. So that gives us a dimensionless constant times joule seconds right there. So the joule is energy. So if we have mass, oh, excuse me, if we have, I'm trying to, oh,
And then there's a
realizing
meter
this might be,
squared.
this is kind of self-referential here.
Well, a joule is what, like a kilogram
It's it's
times
literally
meters squared or
kilograms
something.
times meters squared divided by seconds squared. It's an amazing thing. Like the joule threw me off before I really started to like look into this because I was just going through a calculation on Wolfram Alpha, and it's like it says approximately like 6.3 relativistic mass of one joule. I'm like, joule has a mass. I thought that was energy. You take a joule, if you divide it by c squared, you get the magnitude of 1 over c, which is an interesting thing because, well, the meter, second, and kilogram, if they're based upon constants of nature, and the joule is literally our energy conversion factor. So that's, or at least when you're dividing it out, because at first I saw it, I'm like, okay, so why is like the inverse speed of light squared here? And then after going through the definitions, I'm like, oh, this is why. Um,
So this 2e over h, what is the e? Is that like the charge of an electron?
Elementary charge. Yeah. So it's charge of either an electron or a proton. Um, Typically, this is the electron unless otherwise stated. But
Uh-huh.
elementary charge, it technically could be one or the other, and you would have a sign convention change. It shouldn't matter for if you're squaring it, but for something like this, I think that would have somebody can correct me. I think that would just depend on the direction of current flow, so to speak.
Sure, sure. But this is taking advantage of a very arbitrary fact about our universe, which is every electron is equal in every aspect that we can measure them.
See, it
We should
appears to
be
be a
so lucky.
constant. Exactly, exactly. It's like I don't know. Maybe it's better to be lucky than good. Maybe we just got lucky. Okay.
I think it's remarkable
So
and very fortunate. I
it
mean,
is.
also like the speed of light, same speed in every observer frame. That's very fortunate because that comes up in the
I mean,
definition of the meter and all that stuff.
yeah. Okay, so I should probably clarify this. I just kind of skipped ahead. Basically, what we would normally do is we would have H, we would have its magnitude, just a numerical magnitude, and then we would just put meters and seconds outside the parentheses, and we'll come back to do this. So, because I'm realizing now that I'm like, oh, I kind of self-referenced here because the joule already has mass built in, and we're trying to get a mass out. You should only have one thing on mass. So this was an error on my part. So I'll note that, go and update it. Um, okay. So for time's sake, which technically the ampere is, excuse me, charge is actually time times current. Uh, so this is one of those things where somebody really nailed it because the old school definition uh, that was uh, the old school definition about the force generated by a constant current between two straight parallel wires placed 1 meter apart. It was the initial definition. We started using some silver nitrate fluid with basically we had a little glass jar. We would have some uh, fluid that had a particular amount of, I believe, silver nitrate in it and everything. Then they would have a current through. It would gather on one of the anodes, and then all of a sudden they would actually weigh the amount of silver that came out. Um, they ultimately just ended up going back to the original definition, um, and then they basically defined it now as we talked about a little bit before, it's the ampere is literally 1 coulomb divided by seconds. And the coulomb is based upon uh, elementary charge or 1 volt divided by 1 ohm. Um, Something I just want to highlight here, and again, this is the benefit of the Wolfram database because it probably has one of the largest collection of units. I think Stephen at one point said it had like over 10,000 different units. I have no idea what these different things are, but the interesting thing is you look at some of these things, it's like, okay, these just 10 relationships, and then you're like, wait, stata amperes. Wait a second. This
Yeah,
appears to be
unit
the string of
officially
digits of the speed
deprecated.
of light. Yeah,
Oh,
exactly. It's depreciated. I'm like, wait a second, this is depreciated too. I'm like, is
deprecated, yeah.
is there
And
some
so it's like this is an old unit that's no longer standard, used as
but
a standard
I mean
anymore, I
it's
guess.
but
But
it's I am of the mind that like isus and emus they are underutilized and underappreciated depreciated units.
what's an
Um,
emu? I want to know that. I want to know what an emu is.
oh, it's like isus except what is it? I think it's off by 9, 10 orders of magnitude. Oh, uh
I mean, they're not talking about the animal, are
no,
they?
no, 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 no. It's no, we're not talking about any wars in Australia or anything. No. Not those emus. It's I don't even know. It's something good question. Somebody should look it up. Okay. And then we could also redo that as 1 volt divided by 1 ohm. And we get those things. And Wolfram Alpha also has basically the atomic units in that particular reference thing. You have to do a little click down, make sure you're just in the right dimensions. All right, now we're
On
getting
the
to
subject of
temperature.
I'm
Hopefully we can
sorry, on
answer.
like a
Oh,
coulomb or an
yes.
ampere, right? So
Oh,
like there's
please.
an amount of charge, and then there's like a rate of moving charge along a wire or something like that.
It's charge per unit of time.
So I guess the practicality of measuring like charge per unit time would be, I mean, once you have like flowing current, then that induces a magnetic field, which that you could then use like something that responds to that magnetic field as a force, and you measure the amount of that force. So as long as you have like a kilogram defined, then you can measure um, coulomb or amperage or current flow based on that, and then from there, then you can like say, okay, well, as long as I have a certain amount of current going, I can aggregate that amount of current over time and get an ampere,
Right.
something like
And
that.
this is how we have it parameterized now. I'm not saying this is the be all and end all, and like some folks have kind of brought up. I don't think for a lot like for commerce and stuff, okay, maybe you want the candela so folks can figure out how bright things are, but I think you can boil it down to probably about five, as long as you have a notion of time, a notion of length, a notion of mass. Then you could probably go either current or charge, and then you have to have temperature in there. The mole, personally, I think, at least with modern computers and stuff like that, I think we can count. That might be a little bit redundant, but then again, I don't want to take away from anybody's flair, and I don't want the chemists to get mad at me. So you can have your moles and use them too. Okay. Oh, the one thing I did want to point out here is uh, basically we have Ohm's law, which appears to be I is basically current equals voltage divided by resistance, which is all 1 volt divided by resistance of 1 ohm. Um, but these definitions relate to elementary charge and the Planck's constant to verify current and voltage value. Note, Ohm's law is empirical. It's based upon experimental observation. And talk about getting lucky. Ampere's constant is literally precisely defined at 10 to the minus 7. How could we be so lucky? Now, the interesting thing is they're probing along around like I think about the seventh or eighth decimal place there. And maybe it holds. If it didn't, and it was just a little bit of deviation because there was a good period of time where we thought the speed of light was just three times 10 to the 8. And for that period of time, we had the speed of light right to like zero significant digits technically. Uh, eh, 200 and not 2.9978 times 10 to the 8. It's until you have that precision, it seems pretty close to 3. And for many calculations, that's probably good enough. But if you're trying to calculate something to 14 significant digits, like the anomalous moment of the electron, you want as much precision as you can get. Okay. Temperature. Okay, so thermodynamics, number one, if you're interested in this, you should probably read Stephen's post on the history of thermodynamics, where a lot of how we got there and everything was the inspiration for the title of this post. Um, they had a number of different methods used from what is this hollow sphere filled with air, trying to see the change in temperature, and these were rudimentary thermoscopes to see as temperature would change. Basically, it would start to almost just kind of suck it up there. Uh, so yes, and this was, as Damaris was saying, uh, during the 1600s, the Grand Duke of Tuscany noticed pressure also affected said thermoscopes, an effect that helped later develop the ideal gas law. Okay, and then we had early predictions of the minimum temperature. We again used water as part of the scale for, uh, oh, actually, Celsius, who a lot of times we have some of our more modern public scales named after. His original scale was inverted. 0 was the boiling point and 100 was the melting point of ice. So we just kind of flipped that, and then we're still using it today. Uh,
Was that because what
Newton
he
had
at the beginning of they didn't know like what was heat and what was cold. They thought cold was a substance that flowed and you know like came down.
I think it was heat. We had the theory of caloric fluid. I'm
Mhm.
realizing now, just say have those words come out of my mouth, I've done a disservice, and I completely skipped over um, the whole Carnot revolution and everything like that. I think Steven covered that pretty well. But again, it was the idea that, well, the heat seems to flow. What seems to flow? A fluid. The idea of caloric fluid. It makes a lot of sense and everything. We later found out well, that's just, was it the kinetic vibration of all these different little molecules, perhaps occupying these different microstates and everything like that. And we're going to get the Boltzmann in just a second to go over that. Um, but it was a logical thing at the time. It's like, well, these are things that we have, and I know that Stephen has proposed that he's postulated that perhaps something like dark matter may be the caloric fluid of our time, and that we're conceptualizing something, and maybe if we could reveal something a little bit more, it'll be like, oh, of course. So, but that's conjecture. Okay. So we have our other different scales there. So was it Lord Kelvin on an absolute thermometric scale to first calculate the minimum temperature of negative 273 degrees Celsius. And then we adopted the Kelvin as the base unit for temperature, and they set the reference point at 273.16. I think it's now defined at 0.15. Uh, where again we use the triple point of water at one point there, uh, because water apparently is very useful, and it's now defined by Boltzmann's constant. So we plug that in, and well, by definition, you're going to get out 1 Kelvin because Boltzmann constant is, well, joules per Kelvin. So if you're solving for 1 Kelvin, you're going to get the the same magnitude of Boltzmann's constant. Okay. Again, stop. I'm going to start to accelerate through again. Stop me at any point of time. Um, okay, so the mole. Maybe this is one of the biggest shout outs to something that's like survived the test of time. Amadeo Avogadro, lawyer turned chemist, asserted that simple gases were made of molecules and also theorized the concept of atoms, so to speak, using the term elementary molecules. So the mole was based upon the number of atoms in 1 gram of oxygen initially, and a lot of us growing up, it was based upon 12 grams of carbon 12. Uh, and the problem you ran into is it was based upon that whole platinum iridium cylinder locked away in Paris. Okay. So basically, as we learn more, and there are other ways to do this. Um, so basically, they started using, basically, if you knew how much mass something had, and you can account for its weight via gravity and everything like that. If we have modern infra infratrometry, basically, we should be able to actually see how many different things. Basically, if you have a single thing and it's in like a lattice structure, well, we should be able to calculate how much that is. So now they have like some smooth balls of silicon and everything like that, where they're attempting to replicate that. But you can also do basically utilize an earlier Kibble bounce there to basically have, okay, if we're calculating a mass of a thing and we're going to break it up because we can count and figure out how many of these things they are, we should be able to actually have some precision there. They actually give this on this website where you have this thing as its definition of a oneness of a mole, where it's like fine structure constant squared times the mass of the electron times the speed of light divided by 2 Rydberg's constant divided by Planck's constant, which I'm like, well, these things just equal one, or equivalently one Avogadro's constant of entities there. So um, it's not maybe the greatest definition. I personally think we can count, but again, I don't want to take anything away from chemists if it's very useful. And also the redefinition, I think it slightly tweaked the value of the atomic mass unit, I think around the 10th significant digit. So more or less the same, but if you're doing very high precision, some folks have voiced some frustrations. All right, the candela, arch nemesis, playful. Uh, it's based upon the luminous intensity of a candle. If you put in candela in Wolfram Alpha, it's going to say like the luminous intensity of one English sperm candle because it's literally based upon a candle. So
With a
this is one of the
specific
ones where
fuel, I guess, the sperm whale grease or something like that.
it's well, I mean, if you're whaling and you're getting the blubber and you're gonna start to craft different candles and soaps and stuff, people work with what they had and everything. Um, Personally, I don't think we should be hunting whales as much. I think they're pretty cool, and the orcas seem to be fighting back, but that's another story. Um, so the Candela is the only unit that's literally, it's based upon a human reference frame. At one point, they literally say it's literally eyeballing it because it's based upon you have two eyes, you have a candle. How much of a plane angle and luminous intensity shall you get here? Uh, it's useful as far as things like astronomy go. Like, so if you're trying to measure luminous intensity, um, and again, they're going to use, if you're an actual astronomer or cosmologist, you're going to analyze the full spectrum of light and not just the currently defined 540 hertz, excuse me, 540 hertz, excuse me, 540 times 10 to the 12 hertz wavelength of about the visual spectrum of the human.
What? So that's interesting. So it's like you have a candle, it has a very specific like wick size, let's say, and a specific fuel type, and then you have it burning, and then you say, okay, it's the amount of light flux coming out of a particular like region at a particular distance away from that.
And that's what they're trying to capture here, and that's why we have the 1 over 683 watts per steradian to try to account for that human factor there. I may have misstated that because that's the best I've been able to deduce because um, this was the old definition, and they updated it basically by, I think, adding in the dimensions there. But in 1979, the candela CD is the luminous intensity in a given direction in a source that emits monochromatic radiation of a frequency 540 times 10 to the 12 hertz that has a radiant intensity in that direction of 1 over 683 watts per steradian.
Okay, and
Try
the
saying that three
radian
times
is
fast.
a measure like the radian.
Solid angle.
It's a solid
So think
angle
like
on
a
a
like
on
a
a
sphere. So
yeah.
think of like a sphere. Yeah, it's a three-dimensional radian. Yes. So okay. Um, so basically, yeah, as they said, they're literally eyeballing it. So if you want to get that out, you can just do 1 over 683 watts per steradian. If then you would put in your angle there, you could put it in 4 pi, x pi, or something like that. As long as you're greater than 0 and less than 4 pi, you should be all right. The 1 over 683 is the average, what an average observer like us would take in. Okay. So now that I've put everyone to sleep over the past hour, let's get into the good stuff. The actual methodology in Wolfram physics.
Right.
Any questions? Okay.
I think we're good. Good to go.
All right. I just want to caffeine up. All right. So basically, as I said before, I was originally just going to do a little bit of a history of units and then try to go into kind of an observer theory and just like try to imagine something. I did not, I literally said in my progress report, we don't expect to find anything meaningful. And then after sitting down with Xerxes and saying we need to focus on energy and momentum through the hypergraph, and then Stephen assigning me homework, while working through that homework, I noticed I'm like, well, the answer I got from Xerxes, it's like really big number, and it seems to be around the magnitude of what is being used in the physics project. So as we can see from the website, it says anything we directly observe must ultimately have a signature in the causal graph. And a potential hypothesis about energy and momentum is that they may simply correspond to excess fluxes of causal energy, causal edges in time and space. Okay, and then you can go to the website that we have up here for the physics project. Uh, okay, and then we were going through our. Okay, well, I'm actually going to read this. Standard quantum mechanics in effect defines h bar through energy equals h bar times frequency. Well, I think that should actually be h technically because it needs the cycle. But in this relationship, energy is measured energy, not the associated energy with a single causal edge. And to convert between these, we need to know in effect the number of states in the Branchial graph associated with our quantum frame, or the number of nodes in our current slice through the multiway system. We will call this number G. So we have an alternative interpretation for determining Xi. Our original technique, again, it was off by 17 orders of magnitude, but when I did that calculation that Xerxes gave me, we took the Planck intensity, which even on Wolfram alpha will give you return uh, energy flux. We divided the energy out, and well, maybe it should have been obvious. It came out to in the interpretation of flux. So you could refer to this as Planck flux, or if we were to strip the dimensions out, what I would claim, at least in this, that perhaps it could be that capital G there. Okay, so basically it gives you this giant number, 7.1 times 10 to the 112 inverse meters squared of inverse seconds. All right. So energy rate per area per energy unit. If that's, I think that's right. I'm open to any comments or improvements. This is a dimensional number though. So I literally did the naive thing and divided out the reference dimensions. I'm like, all right, well, let's just divide out meters squared by time. And it gives us It gives us this value here. So our 7 times 10 to the 112. Okay. What the heck does this mean? This is just some numerology here. Okay. You could make the philosophical argument that if our hypergraph structure is the literal underlying medium for flux, we may take this dimensional count as it appears. I mean, it's quite reckless. And again, we caution, this is speculative, but when I look at this, I'm like, well, a hypothesis about energy and momentum. And I followed up with Stephen after that. It's like he's like, no, this is how it must be. And I'm like, okay, well, the calculations seem to agree with you. Um,
So what's being
and
fluxed?
again, it's
Can you scroll back up to that like quote by Stephen?
yep,
Fluxes of causal edges in time and space. Right. So it's like
okay.
this is I'm just spitballing here. But you have like this, you have space, empty space, let's say,
Hmm.
and it's like it's stitched together by discrete atoms of space in a graph or a hypergraph sort of way. Neighboring points of space are attached to each other in a particular way, and embedded in that space are like objects like electrons, let's say. So an electron might be um, a region of space that has like more structure to it, more edges to it.
Hmm.
And so the movement of electrons would over time be like changing that little piece of space and
We'd have
moving.
some notion of rewriting as it's the electron or what we consider to be an electron is doing its electron type stuff.
Yeah.
So that's ultimately it's I'm trying to see if we can hone in on something and then via smarter people than myself be like, if we notice some interesting form seeming to take place within our hypergraphs, if we could attach something to it and be like, we could try to quantify it or quantify that interesting, maybe it's like a tangle or something like that going on, but we should be able to identify. And then if there was some there, we could try to actually start to quantify things. And ultimately, the ultimate most charitable thing is at that point, if we know modern physics as we know it, we should be able to replicate basically everything and then hopefully beyond that. And again, that's a grand statement. That's the ultimate goal. Is this the method for doing it? I don't know. It's this is a particular method that seems to perhaps some have some arguments in its favor. And if this was following the Wolfram schema, actually that big G number there, it literally is the Planckian dimension of flux. And we're going to get into the interesting thing in the section that you inspired, Dugan. So, okay. So we had da da da. Okay, we went through that. And so we start to plug in these units. So the way the physics project calculated these units is basically you took that number, which was a really big number, you take the square root of it, and then you just divide it into Planck units. So when we did that for length, we had the Planck length. We're dividing it by the square root of our big G there right there. Gives us meters, and it gives us an elementary length of approximately 10 to the minus 93 meters, which was interesting because it was within about one magnitude of the initial physics project estimates. So I'm like, all right, well, that was kind of cool. The weird thing is the initial estimates were calculated in a completely different way. They're using a logarithmic plot of uh, estimating she as then they had this is like a logarithmic kappa number and stuff like that. So basically you have the Hubble time, you plug this in over here and then you divide by the elementary time. So it's uh, basically over here, I would go to the original page for the full calculations and everything. But basically, once they put that in there, as you can see here, we have an enormous number. So starting from one and then going to about a magnitude of three, it's an extremely steep curve. So if that k within this logarithmic structure there, and again, it's I'm not a mathematician. I'm kind of spitballing the best I can, but basically it would be one, but as soon as you start to deviate from one, uh, for instance, 1.01, where are we at? Well, technically the magnitude that that number comes out to be because we're at about 10 to the 112. If you deviate a little bit more, it just keeps on going up and up and up. So we're kind of at the lower end of the estimates there. So we're at least in the ballpark, so to speak. We continue onward. We divide that into the Planck time, and it gives us elementary time of about 10 to the minus 101 seconds. So normal Planck time is about 10 to, it should be about 10 to the minus 44 within seconds there. Uh, but it sounds like, well, if we believe there is something under the Planckian scale, well, maybe this is a way forward. And we do the same with energy, and yeah, we get about 10 to the minus 30 electron results. And again, the reason we followed this path was its seeming ability to replicate initial physics project estimates. I was sitting next to Nick as I was doing my homework, and all of a sudden I'm just kind of looking at this. I'm like, I do some calculation. I'm like, look, this, he looks at this. It's like, well, that number's really close to that number. I'm like, he seemed to be getting a little bit excited. So I'm like, okay, let me go through and see what might be going on here. And again, caution, it's like, I don't know this. This is a coincidence. If it was more than a coincidence, again, how could we be so lucky? Um, so how do we try to interpret this? Because initially it's like, all right, if we have some notion of flux, we're looking for the excess flux throughout our hypergraph system here, and that we have some notion of whether it's empty space might not necessarily be the best term because we have like a vacuum, but it's technically not a vacuum. There seems to be some stuff going on. So that I've heard Steven say it's the constant rewriting of the network itself. And then we would look for deviations within that that would correspond to what we may believe are particle-like things or excessive oscillations in the field corresponding to momentum and energy. Uh, when we do that schema for the rest of the units, we get all these units here. So all these are approximately within one magnitude of the initial physics project estimates here. Go through here, and these are really small numbers, and I could imagine that, well, if we're going to go below the Planck scale, that we're looking for some minimums of things, this would be it. So again, we should note that people very often think Planck scale, really small. I would claim it's a limit or boundaries within reality as we know it to our current conceptualization. The reason why I say that is because you have like you have the elementary length or Planck length, 10 to the minus 35 meters, really small. Everything is Planck temperature, it's 10 to the 32 Kelvin. We would instantly be all vaporized and probably not even have any atoms or anything left. It would just be elementary energies right there. So that's why I'm going to say it's a limit. Also, if you divide an elementary unit of length by an elementary unit of time, you get a maximum of speed. Because if you divide two minimums of something, well, you're going to get a really big number probably. Uh, so these were the initial estimates, elementary length, 93 meters versus, excuse me, 10 to the minus 93 meters, 10 to the minus 92, 10 to the minus 101, 10 to the minus 100, 10 to the minus 30 electron volts, 10 to the minus 29, mass, 10 to the minus 60. Okay, I did that. I didn't go through all these. It's the crazy thing here is I would literally just put that number in there. I don't know, and I don't necessarily have enough confidence to really do that. Um, and again, there are certain constants of proportionality. So the elementary length divided by the elementary time, it's going to return the speed of light because no matter what that big G scaling factor is, if you're scaling them by the same amount, well, Planck length divided by Planck time gives you the speed of light. And that's, I don't know, it seems to be a very useful thing. And that's just the difference and magnitude there. So uh, this means that certain relationships between the building blocks of our world have fixed relationships. And this leads to the notion of coherence within whatever system of units that we choose to employ. Here is an added note that we you if you naively do this to any unit within the Planckian realm, so to speak, it doesn't work. Um, because for these units above, it seems to work. If you just naively divide that into the Planck power, which is a much more ginormous number, you get like the oscillation of like a quartz crystal in a wristwatch, which doesn't seem to be a minimum there. Um, Now, the only difference is, and maybe this is something important, maybe I completely missed it because a lot of Planck units, they're the square roots of combinations. Very often, the speed of light, h bar, Planck's reduced constant, and then big G, the Newtonian gravitational constant. So they'll put those in different forms, different powers, and everything. And they'll take the square root, and then they'll get a single unit of dimension out. Certain things like the Planck power and the original way we computed this potential Planck flux, those really high numbers, when I looked, they didn't have square roots. There was like c to the 8 divided by like 8 h bar squared divided by c or something like that. So those were not the roots of some numbers. If you were to take the non-square root of big G here and divide it in, oh yeah, it's going to be really small. It's going to be really small. So that's something to keep note of. Um, Maybe it's telling us something, but I'll continue for time's sake. So coherent units. So here's basically the whole main pitch. Once we have a coherent system of units such that F equals ma, so force equals mass times acceleration. Okay. Then you can have a notion of energy, which is force times the distance. And then once you have that, you can have power equals energy divided by time. Okay. I said a bunch of words. If you haven't looked and thought about this, it's like, what the heck is going on? Don't worry, we're getting through it. Okay. So sometimes you'll say I've heard Sean Carroll at some point or another say it's like, oh, once you have F plus MA, you can basically redo all of physics. It's be wary of all-encompassing terms. And again, I love Professor Carroll. I've learned a lot from him. Um, but if we're trying to search for the underlying machine code of the universe, in physical reality as we know it, we want to latch onto something physical. Okay. So the reason we're talking about this is just a real quick discussion. All right, force equals mass times acceleration. I use the example a clothes dryer. Some of us have those things. If you were at the summer school and you had to use it, maybe you were infuriated, maybe you were very happy. I don't know. But think about this. It's not hooked up. You have a barrel. You give it a nudge. All right, you gave it a force. Now that massive metal cylinder slightly accelerates. Okay, but you don't just want to give it a nudge. You would like to have it like go through a cycle. So you're going to have that force times a distance. You want it to go around. It's like, okay, now we have a notion of energy. Now, again, the thermodynamics of cooling it aside and everything, but if you want it to keep tumbling and get your clothes dry, you're going to need that energy over a certain interval of time to have it continue going. So just this is just a little bit of an exercise to try to just prime observers like us to be like, okay, it's not just, oh, here's some fancy math. Like there are ways to try to start to intuit it for at least observers like us. And again, that may depend on our scale of reality. Fortunately enough, we live on the scale where we're of the magnitude of the Planck momentum. It's like 6.25 to the first power in Newton seconds, or I would argue we should probably name it after we should name it Noters after Emmy Noether because, well, that's how we're able to do a lot of this stuff, but that's a personal preference. Okay, so we use that analogy because initially uh, Hatem had focused, he's like, you should focus on energy. See what you can parse for this. So as we're going through energy, it's like, all right, well, let's just take our elementary energy divided by time, or actually, excuse me, these are in Planck units, but within Planck units, these should actually end up coming out to be a similar thing. Uh, Energy divided by time equals watts equals Planck power. Energy times time equals the unit of action, h bar. Energy divided by length gives us force, Planck force. Energy times length equals bending stiffness, which was something that I did not know before this project, which is the h bar c convention, which is another interesting thing to get into at another point. Um, so we went through there. Okay, we're going to start to wrap up here. Maximum entanglement speed. And this is from the units and scales that you can find there. So we have 1 over time, elementary time. It gives us frequency. This is from the initial physics project estimates. When we go through and do that calculation there, we get an elementary time of 10 to the minus 100 seconds, which convert the frequency is like 5 times 10 to the 99 hertz. Extraordinarily huge number there. But Stephen had postulated you would want to think about this as perhaps a maximally entangled observer. The maximum entanglement speed is claimed to be zeta in regards to the associated energy with edges in the causal graph would be elementary energy divided by elementary time. And it gives you this huge ginormous number. All I did was go in and actually plug in the actual units without just the magnitudes. Uh, and it comes out to look like the Planck power. And I'm like, how did you know this would be the Planck power? He's like, I don't think I did. So, but this is going to be a relationship that would hold because it's a minimum of energy divided by a minimum of time. You're going to get a maximum of power. Okay. So, and again, this is because of coherent units. Just for reference, the output that they have here is something like 10 to the 52 watts. That's 10 to the, that's about, what is it? Like about 100,000 solar masses a second. So basically, this output for a claimed maximally entangled observer would output the mass energy of Sagittarius A star, the what is believed to be a supermassive black hole in the middle of our Milky Way galaxy. It would output the total mass energy of that in 21 seconds.
That's nothing.
I mean, that would be a
Just
lot of
kidding.
something. I mean, it's
That's
what the heck
huge.
that might be.
The mass energy of Sagittarius A. Yeah.
It's 4.3 million solar masses. I think we have it.
Is that the one at the center of the Milky Way?
Yeah, it's 8.5 times 10 to the 36 kilograms. Earth is about 10 to the 26 kilograms.
Okay.
Yeah, that's uh that's a lot. What that may or may not be, I don't know. I could speculate, but that's for not for the purpose here. Let's get to Dugan's section. Hypersurfaces. And this was the kind of the point that I completely missed. We go to Math World. So we notice it's a generalization of embedding 2 dimensions within a 3 dimensional space. We extend that to n minus 1 dimensional surface embedded in n dimensional space. Okay. Then I'm like, oh my God, I'm so dumb. I'm like, well, wait a second. Our dimensional term for that big G there, the Planck flux, we have 2 dimensions of space and 1 dimension of time. If we believe we live in a 3 plus 1 dimensional space-time, then by our definition, this seems to constitute a hypersurface.
Hmm.
Um,
Mhm.
which, if we go through, this actually kind of makes sense because if we take this dimension of Planck flux, so to speak, and then just using Planck units, we multiply it by its equivalent energy, well, basically we get the Planck intensity or the maximum energy flux. When we do that for momentum and we multiply by the Planck momentum, we get the Planck pressure because that's okay. These are maximums that if we were to encompass either that Planckian intensity or that Planck pressure, if that happens within a Planck volume, you're going to basically create a black hole or whatever we assume to be a black hole by that extent because that is the maximum there. So when we put Planck or elementary units through this dimension of flux, or this, in this case, we would consider this a time-like hypersurface with energy. And then within momentum, we would consider that a space-like hypersurface there. And again, I'm not a mathematician and don't have a PhD in physics, so I'm like, anybody has any any notion of what is actually going on or how we could apply this, I'm open to all comments and everything about how we could try to figure out what's actually going on. But I literally didn't notice this until I was
Well,
going
no, that's interesting
back through
because
here.
like the idea was to measure like a flux of something, right? A flux of like hyper edges or updating events or something like this. And
The
so like
excess flux. So I'm
uh
imagining you would already have some network written, and then you would have some notion of change or energy flowing through a particular given amount of area or volume, and exactly how this would work is it's beyond me right now. I just kind of noticed that this seemed to line
right,
up
right.
with
So like you have like a volume of stuff happening of energy, and then you want to measure how much of that energy is uh transferring through the surface area of that volume. And the surface area of that volume is precisely a hypersurface in the dimensionality that you're working in. So if we're in 3 dimensions of space plus one of time, but 3 dimensions of space, spatial extent, then you're gonna be working with a 2 dimensional surface area and measuring the the transference of stuff going through that over time. So that's why it's a like I said, hypersurface in our dimensionality, and that's 2 dimensions. Two dimensions relative
I
to
mean it's
three.
an interesting thing because
Yeah, yeah.
yeah, no, if you're yeah, because if you're calculating any type of surface or anything like that, even technically a four-dimensional hypersphere, you might have a content of 4 dimensions. It still has a three-dimensional surface area, or like we said, just with a normal sphere, you have a two-dimensional surface there.
Mhm.
Uh, what particularly this means, I mean, just my initial thoughts uh, were I thought of the Bessel function because we have a nice little image here. Where will it work?
Mhm.
Oh, hold on. There we go. It's kind of like you have a surface, it's kind of like a drum head or something like that, where if you have some notion of oscillation within it, I'm like, it's going to deform there and everything. This is just where my mind had gone to, and it was a cool little animation. So this is again some speculation about what might be going on. Um, the other quick thing just to note is, all right, this dimension of flux, it's inverse time area. That I have trouble parsing that, but you can rewrite this so it's equivalently uh, frequency over area. So you could rewrite this as Planck frequency divided by Planck length squared, and it's equivalent, or at least according to Wolfram alpha, it's equivalent. But so I'm like, all right, so we have some notion of a frequency area. I don't, anytime I have frequency, and I'm very biased here, I think of like the clock speed and everything on our computer.
Yeah,
So
yeah.
it's got a bit of a computational error there. So I don't know, is this additional evidence or am I just painting myself into a corner? I can't say.
Yeah, it's
Maybe
amount
it's
of stuff
Gladrill's
that's
horn.
happening to per area per time. And a per time is the same as a hertz or a frequency, excuse me.
Yep, yep, it's cycles per second. Yep,
Mhm.
cycles per second. So whatever that might be. So again, how are we actually going to try to intuit this? Because it's like, all right, if we have a minimum that we know of in standard physics of the Planck volume, and we're trying to translate this through space and time like hypersurfaces, why the heck does this, oh, excuse me, basically this big she right here. This constant of proportionality, it's like, number one, why does it seem to line up very well? Because this was done in a completely, this is estimating the number of nodes in the graph, but this is being applied to things like on apparently a small scale. What the heck is going on? Could this be the actual total number of nodes in the system? Or would that be, I don't know, maybe the associated amount of ems or atoms of existence within a Planck volume? And if so, what's going on? Because according to the original formulation, This is our position and number of nodes within the system. Now, this, as I at least claim to have derived it here, seems to be a fixed number. But if this does change, but everything is scaled by that same factor, would we even know? I mean, could this be changing? Or is this a form of some constant of proportionality? Or is there some weird thing where maybe we're in some maximally extended state, or perhaps we're in, oh, maybe even crazier, a state of equilibrium, if you would, and this is a settled upon point. And again, these are questions that are still open that I have no idea. And again, this I must caution, this is a speculative result. If this was to line up, I think we could probably start to. I'm just looking for something to physically attach onto. And if the Planckian flux we could translate into the Wolfram Physics Project schema as the actual flux within our network, we should hopefully be able to actually like quantize things. And once we can start to quantize things, relate them to physics as we know it, we should be able to start replicating on ultimately the best scale that we can and hopefully probe further. So that's ultimately where I'm at right now. So I apologize. That went a lot longer than I was thinking,
It's
but
perfect.
questions, comments.
Yeah, it all comes down to mass and movement of mass. Like, what is energy other than you have mass and you're accelerating it, you're changing its like motion. Um, and um, like what is mass to begin with? Like, okay, well, you have quantum fields, let's say, and you know that something is there because there's a spike in the quantum. There's a region of high density in the quantum field, and where that thing is that you have like a quark or gluon, or no, you have like a quark, and something is there because there's a concentrated amount of field strength at a particular location in space. Or
We are
with the
probing into
electromagnetic
reality. Our
field, you know
detector
that
goes
an
click.
electron is there because there's a spike in the electromagnetic field strength at a particular location in space. And um, so it's like, okay, well, what are these fields? It's like you have space being there, and then a field sort of like layered on top of that as like a scalar quantity. The theme of the physics project is okay. Well, you have space that might be made out of nodes connected by edgewise pairs or hyperedges or whatever. And if there's like a concentration of a higher density of that structure in a particular location, then that's like you have a field, a density field, and you have like a spike of density there. So if that's how quantum fields or electromagnetic fields are modeled, then you're looking at varying densities of hyperedges. And so that's kind of what I was thinking you were getting onto with like this. Oh, you're muted. You're muted.
Oh, sorry. Yeah, one of the initial things that I kind of gotten from Hatem and Nick was I'm like, all right, so what could we do? Could we go about counting those edges? And I think Jonathan had developed some things to help model colliding black holes and everything. So I'm like, all right, well, maybe I don't know if it's within our computational power yet, but if we could have a very precise version of that and we could model, it's like, all right, well, so we got general relativity, it's got like precision to 14 significant digits. I'm like, if we could model that and literally count the total number of edges and maybe just insert a number, see what happens, see if it lines up with general relativity as we know it, as far as corresponding values and results. Now, can we count that many edges right now? I don't know.
With a lot of edges, yeah. Hypothetically.
Oh yeah, well yeah. If every Planck area is like 10 to the minus 112, that's a big number.
Yeah. Like, modern computing is sort of limited to the number of powers of two you have inside of your memory modules. which kind of tops out around, trillions at a time for hundreds of gigabytes
I mean,
or
exponents go up
terabytes.
really quick. Yeah.
I know. It's combinatorial explosions, man. But
Yeah.
we
It's,
should be so lucky that we have, computational power that we do. But we're
thank you, guys.
limited to the size of atoms at this point.
Oh,
How many
who
atoms can we
knows?
pack in a memory module?
Yep.
Maybe a question. So you said you actually did a computational experiment where you were counting the edges. So which edges were you precisely computing? I probably missed the kind of in which region, or how did it technically? Because I'm currently doing some experiment where it would actually make sense to actually count all causal edges going. We are having some kind of notion of coordinatization, which we define using graph notion like graph distance and so on. And then we obtain like clouds of points which have the same spatial coordinate. And theoretically, I can imagine computing all causal edges on a in a spatial section of the causal graph. All causal edges going through this one region with all the points having the same coordinate and defining kind of the flux through this coordinate by the number of the edges. So were you doing some similar experiment, or how precisely did you compute it?
Oh, I haven't computed it at all. I'm just hypothesizing right here. So I'm basically just taking what Stephen had originally put down, that if we can have some notion of excessive flux through the causal edges of time and space. So I believe the way that, and again, I'm very naive at this. The way I would consider this is, if I was to take this claim seriously, you could either take the numbers initially computed, or you could take uh, the numbers here. So you would assume that maybe within a Planck volume or Planck area, it might be a little hard to tell. Maybe you might have a total of, within some Planckian unit, about 112, 10 to 112 nodes or something like that. That's why I'm like, all right, so if you had that, and then you were to take your Planck units and it would depend on how you're doing the calculation. Do you have a mass term? Are you computing momentum, energy? Because that would correspond to my knowledge for how it was laid out here. And again, please correct me. Of momentum goes through space-like hypersurfaces, while energy traverses time-like hypersurfaces. I'm not going to act like I know what that means, but that's the what I'm getting there. How that would actually be done, I don't know. If you're actually doing the experiments, I'm open to ideas. No, what I would say is maybe take some of these units here, and if you could run something and maybe like not spend too much time on it, and see if any of these units seem to jive, so to speak, with things that we know within physics in general, that that might be useful. So if all of a sudden you put in 6.065 times 10 to the 92 meters and these numbers here, and you were able to actually start to quantify and be like, oh, well, that looks like what we've observed from this LIGO or some of the simulation. It's trying to find a way that we can replicate in high precision the things that we seem to notice in physics. Because at that point, if we're doing this with a very elementary, at least attempting towards a source code of reality, I mean, at that point, I don't think people can just ignore it, because now you're actually doing it with high precision using software that was designed to do things potentially like this. So I'm not sure if I
Yeah.
answered your question. I'm sorry.
Pavel, I posted a link in chat referencing one of the black hole simulations using hypergraphs projects. I think that Jonathan Gorard helped Jacob Ugary uh, produce, and so I'm
So
not
it's
sure.
it's
Like,
a really cool little animation, and it seems to, I don't know, it seems to line up to the other simulation stuff we have, and it's just from very basic rules. That's was ultimately the idea, the inspiration of that. Like, if we have a simulation, if we could keep track of X number of edges, if we have some notion of the parameters in this, maybe we just literally just kind of do what like the folks at the international system of units and everything did, and just kind of like plug in and see if we can compute something. I don't know.
Mhm.
Yeah, this
Hmm.
here. So Pavel, I guess the sort of edge count here would be on the order of hundreds or thousands for this particular little computation.
Mhm.
Oh, neat.
And I think Luke, did you work on this as well, or do some recreation of this? I think Luke's busy somewhere, but yeah, really cool stuff here.
Neat. All right, I'm gonna have to
Like
take a look at this.
discretization, just hypergraph discretizations of space-time geometries around singularities.
Very cool.
Yeah.
And also in your theory, you were considering only causal edges, or were you also would do you think that any role would be played by hyperedges in this thing at all, or is it only kind of about the one skeleton, only about the edges? What you were thinking?
I have no idea. It's my general notion is again, it's I have limited knowledge on this. I was basically just going through the physics project website, the assigned reading, and I'm like, I'm trying to associate the best I can. If it's something like a space or time like hypersurface, it's like, all right, is there momentum going through it? It's space like hypersurface. If there's energy, it's got to be a time like hypersurface. Um, I think the maximum entangled speed I literally just stole from Steven saying notion through the causal graph. That's why I use it there. If I'm just talking about just a general hypergraph structure, I say hypergraph. I'm not an expert. I was trying to be about as careful as I could. Um, I need to learn more to actively say what's going on.
Mhm.
I'm
It's a
I'm sorry.
Oh, thank you.
yeah, it's a large field of inquiry. I mean, there's a lot of work to be done uh, by a lot of
Mhm.
people, and be interesting to see where this goes in the future.
Hey, if some scrub like me can put together something that might be interesting, I mean, heck, it's worth trying.
Absolutely.
Yeah, I was gonna say for me, like it's a lot of this is beyond me, but um I was really interested to kind of like have this idea of measures be completely demystified by reading this reading your paper and realizing just how relative everything actually is. And it just kind of made me feel kind of more empowered to step away from some sort of temptation to understand all of these measures and their relationships and actually understand that we can potentially leave behind a lot of those traditional measures and just try and focus on kind of some natural concepts or some basic concepts and rebuild from there without needing to kind of defer to a lot of these what feel to me like relatively arbitrary frameworks. So in some of the in what another way it makes me think of grids, like these all these measures are just all sorts of alternative ways of defining grids against which we're then going to model or describe the world. And so, you know, why that particular set of grids? Why not another set of another concept of grid? Um, yeah, so I'm not quite sure what to do with all these ideas right now, but I found it valuable to have the opportunity to sort of survey the history of these measures, understand how they relate to each other, and realize that a lot of this is just a social history of physics that perhaps we can kind of step away from.
Cool. No, I mean, I spent time thinking about humanity for a long time. I'm like, oh, just solid logic and thought, and you can win arguments, and then you find out human beings are very complicated creatures, and I'm like, Well, human beings seem too complicated, so let's try to figure out reality. That seems easier.
I love that. Yeah. One last question from chat. Like, how do we leverage statistical analysis to kind of coarse grain these notions of like edges or hyper edges? Like, would it be possible to employ that kind of reasoning here?
That's my only comment on that is logs are useful. Um, that's my best way of if we're trying to do some calculation and it's going to take an enormous amount of compute and you don't really have that time with the compute power, it's maybe you take a log because the coincidental thing that I noticed maybe a couple of weeks ago, and maybe it should have just been obvious to me, is if you take the logarithmic value, like if you strip out units and you just take Planck values and stuff,
Mm.
if you look at the numbers enough, initially you'll be like, oh, that's the speed of light there, or like, oh, that's h bar, because it's going to be a similar magnitude because it's a coherent system. So you might have some number like 10 to the 112. If you take its logarithmic base and then you take the logs of other things, they're going to line up. So like each unit is going to have an associated logarithmic number, and the combination of those numbers uh, should be the same, and then you could always just exponentiate it back up. I'm not sure if that was the answer, but I'm just trying to think of a way that if you could try to take something that's really big and find a way to usefully use it, I claim logs are useful.
Oh, for sure. I mean, you can really see the trends of you can unexplode things using log plots. And then if you see like on a plot, this exponential curve and then this other exponential curve, and like what are they doing? You put them on a log plot, they turn it into lines that like eventually meet up, and you're like, oh, here it is. Here's the relationship that
I
we're
can
looking
actually
for.
see what might be going on. It's a
Exactly.
useful thing to observers like us. But yeah, one of the other things is I know you had mentioned Stephen had one kind of like an observer theory thing, and it's like I kind of skipped over that because I went down this thread of investigation. Um, I'm realizing more and more that that's an important thing. And we were talking before about kind of maybe trying to set up like a hypergraph. It's like, all right, you have these units, you have these things that we've measured in relationship to those units, and can we kind of like set it up in an intuitive way that we could kind of almost navigate and just see things related to each other on different scales and how different magnitudes may or may not correspond. And that's also something you would probably have maybe some log manipulate or something in there. So that's just an idea for future stuff.
Absolutely super useful. Great presentation. Lots to think